Okay, milling a CO2 Dragster in Autodesk Fusion 360. I'm going to start by showing you around the tutorial folder. Inside the tutorial folder you have a few things. You have the NC files folder. Inside this folder is where we're going to export our NC code to. There's the post processor folder that contains a file called technomill.cps. This file is the post processor file that Fusion 360 will use to convert the code to the language that our technomill understands. It's the 2020 Fusion 360 Dragster demo. This file can be uploaded as an Autodesk Fusion 360 file. It's a copy of the actual toolpaths I'll be creating today in the video. This is a PDF of an outlined instructions for today's tutorial that I'll be referencing throughout the tutorial. This is the video file that you're watching right now, a SolidWorks Dragster example file, it's a part file, and a SolidWorks Dragster example step file, which is an export from SolidWorks I'll talk about in just a second. Okay, first I'm going to begin with a little about Fusion 360. Fusion 360 is a cloud-based design software, so you will have to create an account. You can see I'm logged in at the top. I created my account, and at the following website, if you look here in the tutorial and go down towards the bottom, there is a Autodesk Education sign up. If you click that link, it will take you here where you can log into the free Autodesk Education information. As you make this account, it will take 24 hours or so to verify you as an educator or a student, and then from that point forward you'll be able to access all Autodesk software for free. Inside here, I'm logged into my account. I'm going to save things to the cloud. You can upload things from a desktop, files from a desktop, but once you're in Fusion 360, it's going to have you save everything to their cloud options, which I'll show you more about in just a minute. A little more about Fusion 360. Right now we are in the design workspace. You can see here is the workspace tab. I can change the different options. Right now we're in the design workspace. If I wanted to, I could create the geometry for a dragster right here in this design workspace. But I am going to make my dragster, or show you today how to import data from SolidWorks, like you can see here. Fusion 360 has different workspaces. There's a render workspace, which would allow you to render and create pictures or realistic images. There's an animation workspace, and in the animation workspace, it'll have you actually set up animations of parts and assemblies moving. A simulation workspace will work with airflow simulations or compression or things like that, stress fractures, and any kind of data like that. Manufacture will be working in it today as well. That is where you would create toolpaths and different tool processes. Drawing is where you would create a print of a drawing or animation. So I have created or have a dragster file here in SolidWorks. You can see it's created. I have all the different options available here in the properties menu or the properties tree. I can edit in each one of these independently, and I can modify my car from there. Let's say I'm done with my dragster and I'm most comfortable making it in SolidWorks. I can then export it to Fusion 360 by doing a file save as a step.step or a step file. That step file is a language that all CAD softwares pretty much understand. It's been around for many years. Inventor, Fusion, SolidWorks, they all can deal in step files, and it pretty much transfers back and forth. But when I do open that file in Fusion, I will lose the ability to edit each one of these features independently. So that is a disadvantage. If I would model the dragster in Fusion entirely, I would have that option to modify those things here. But that's just some advantages and disadvantages of modeling and where you create the geometry. But Fusion is great regardless for creating toolpaths and geometry. So let's say I have that file saved. As a step, I'm going to go to File Open from the computer where I have the step file saved. I'm going to open up that step file that you can see right here. I'm going to go to File Open, and it's going to open up, and it's taking a second to convert. If you look here, right now when I click the front view, it is treating this as the front view, which really is the front of the car, but in drafting standards, This view, this left view, would be the front view because it is the longest side of the car, has the most in shape, and is mostly defined, or mostly defines the overall shape of the car. That's just a standard rule in drafting. When you create your 11 by 17 drawing, you're going to want to have this be the front view. I can reset this as the front view by right-clicking on the property square up top, or the navigation square, going down to set current view as front. Once I have that view set as the front, I'm going to do a file, save, and I'm going to save. At this point, I am saving this file to the cloud, to the Autodesk cloud. I'm going to save that into my Fusion 360 Dragster 2020 project. You could create a new one if you wanted to. I'm going to call this, name of this file, Fusion 360 Dragster 2020, and I'm going to put a 2 after it because you can see I already have one here that has a 1. Let me make those file names match a little bit. Okay, and that is a number 2 there afterwards. So I'm going to go ahead and I'm going to hit save. So now that file is on the cloud there, as you can see, and I have a version number as version 1. It does update, and you can see every version of your file from the you can go backwards and see them. If you happen to make a mistake, you can go back 2, 3, 7 versions ago and see every save along the way. So now that I have the dragster in here in the correct view set at the front, I'm going to begin by setting up some sketches and bodies or solids I'm going to need to create. The first thing I'm going to create is the stock itself. Alright, I'm going to start by creating a sketch on the right plane, and as I create that sketch, I'm going to create the stock or body that you started with to create your dragster. I'm going to just draw the rough shape of the sketch, and then I will add in the measurements that I need. We know that the height of the dragster is 70. The height over here, and I did rotate it around, just give me a second there. Get back to the front view. And this number up here is 20. This number down here is 305, and you can see as I put in this 305, it does lock all the geometry in. It is now all black and fully defined and linked to the origin. From there, I'm going to want to extrude this into a solid, so I'm going to finish the sketch. I'm going to rotate it, and you can see that that sketch is actually on the center plane. That's right where it should be. So I'm going to go ahead and extrude a 2-side extrusion, 41. And I screwed that extrusion there up. That sketch should still be there. Okay, so I'm going to go ahead and I'm going to, I undid or Control Z that extrusion. I hit enter too quickly there. So I'm going to select my sketch. I'm going to select 2 sides, 41 in that direction, 41 in that direction on both sides. Oh, sorry, 21 and 21 to equal 42 total millimeters. See how it's default to cut? We're going to want to go and switch that to new body, and we'll create a new model or new body. I'm going to click OK from there. So now you can see I have over here in the property tree body 1, which is the car. So I can actually go ahead and rename that car. I have body 2, which is the stock. I can go ahead and rename that stock. And I'm going to rename this sketch. And when I went back into it, I'll exit real quick. I'm going to go ahead and rename that sketch as well. It's the stock sketch. Okay, from this point, I can go ahead and I can turn the stock on and off. We're going to cut that car from that block of wood. I have it turned off for the moment, but I'm going to turn the sketch on. We are going to make one more containment sketch. Okay, and we're going to call this sketch the side cut contain. And you'll see what it looks like here in just a second. I have the sketch turned on for the stock for a reason. We're going to need that sketch to reference some points on it. I'm going to start by going to sketch in the right plane, or sorry, the front plane where we are, and I'm going to go ahead and draw a line up. I'm not going to connect it to any of the points on the sketch from the stock, but I'm going to mimic the shape coming back down to the line and then closing the loop like you can see here. I'm then going to add some relationships. All the sketch geometry is blue now. I'm going to define it and make it black by linking it to the stock sketch that is defined, to the origin here. I'm going to start by clicking coincident to add a constraint or relationship. I'm going to click coincident, click this corner point, hold control, and click the corner point of the sketch. It'll lock them together and start turning some of the geometry black. I'm going to do the same thing on this corner. Okay, and I am then going to go ahead and hit escape and click the parallel constraint option, hold control, and click that of the line for the angle here and the same line in the sketch. I'm going to then do that here and here. Now you can see everything is kind of lined up in black and defined except for the length from the front of the car to the back of the car. And how do we know what this value is going to be? We are going to leave an actual exclusion zone here. Okay, and you can see here that exclusion zone is going to be like this. We're going to leave 15 millimeters that we're not going to cut here at the front of the car. And we're going to leave that so that the block can stay attached in the mill in the fixture so it's held in place. Okay, so how long do we make it? Well, if we want to leave 15 millimeters, we'll dimension from the front to the back of the sketch. And I know that my car is 240 millimeters long, and I'll subtract 15 from it, and I'll get 225. And now that sketch is defined, and I have my side cut that I want to cut. I'm going to finish or exit sketch, and now I have sketch number 2 that I'll rename. And I went in there again, I'll exit, and then I'll rename that side cut contain. And from this point, I can go ahead and I can turn off both of those sketches. I won't need to see them for right now. And we're going to go ahead and we're going to change the document units. Because from this point forward, we've been running in millimeters, which is the units we use to create dragsters. But if you see down at the bottom here, there is a mill setup reference page. Mill, it talks a little about the mill and the type of the mill. We have the Techno Da Vinci CNC servo model. And you can see here that the machine units are set in inches. So we're going to need to create our code in inches. It's no big deal. We don't need to convert a bunch of stuff. We'll just have to change the units of the document to inches. And we'll reference this machine axis orientation here in just a few minutes as we're working ahead here. So we're going to change the units under document settings from millimeter to inch and click OK. From this point, we've been operating everything in the design workspace. We're going to go ahead now and switch to the manufacture workspace, or we're going to create the toolpaths. So we've gone ahead and we've moved there to the manufacture workspace, and the units are actually set in each workspace separately. So we're going to go ahead and switch the machine units to inch. All right, so we're going to switch the machine units to inch, and we have that set in the inch setting. And we're going to go ahead and we're just going to start creating the tool setups. So if you look at this dragster, it's a little, it has some geometry on both sides. You'll have to cut the left or driver side and the right or passenger side of this dragster. I use the driver and passenger references because it makes it easier for me to understand and not get confused left and right. And you can also see here that the bottom of the car itself has geometry that will need to be cut out. If you do not have internal wheels or the slot like you see here for the fishing line to travel through, or a weight pocket to cut out weight, you wouldn't need this bottom cut, but I'm going to show you today how to create the bottom cut if that would be necessary. So we're going to start by creating a setup for this bottom cut. And as we're creating this setup, we're going to have to pay attention to the machine axis orientation. And I here have a picture or graphic created. This is an actual picture of the CNC mill, the servo model in the classroom, and here are the 3 axes. You have your X, your Y, and your Z. And you have a positive direction. X positive runs out of this motor in this direction, so X is positive always that way. Z positive is always away from what you're cutting, positive direction Z, and Y is always out of the back of the cartridge hole or back of the machine. Here is a picture pointing to the cartridge hole on the machine. You can see here's the block that we're cutting, here's the small end of the block, here's the large end of the block, and here's where it's held by the cartridge hole back here. That is the origin, or 000, that we treat our file as, the back of the cartridge hole right there on the back of the car. So I'll now go ahead with the tool setup with the X, Y, and Z orientated correctly to where the Z is going away from the bottom where we want to cut at. So here we go. We're going to go to New Setup. We're going to go to Select Z axis / Y axis. Now the first thing we're going to do is change origin to selected point. We're going to select that point, not the part origin. We're going to select the origin that we want it to be, or a selected point, that cartridge hole in the back. I've now selected that cartridge hole. Now looking at the image that we're referencing, we need Z to be positive away and Y be out the back, or point out the back of the cartridge hole. So here is Z. It wants to know which way Z needs to be, and now wants me to select Z. So I select a line perpendicular to the axle holes, and that'll put Z positive away from the bottom or where we want to cut, and Y is out the back just like we want. Next we need to select the stock. To select the stock, I go to Select Stock from Solid. Alright, and then I select over here by opening up the model, the dragster, the body. I select the stock body. Doesn't need to be visible. I can still select it. I select that body and I click OK. Here we now have a setup for the bottom with the X, Y, and Z the right way. I can rename that setup to be bottom cut. Alright, so I have a setup for the bottom cut now created. Now from there, I'm going to go ahead and start creating my toolpaths. I'm going to do a file save real quick just to get the file saved so I don't lose with my settings here. And you can see I now have a version 1. So I have a version 1 and a version 0. A version 2 and a version 1. There's the version 2. We're going to go ahead and we're going to move on to creating the actual adaptive cut, or the clearing, begin cutting. We're going to create this toolpath, and we're going to need to do that using set up a tool. In the tool settings, in the tutorial, if you go down to the bottom, there is a tool setup settings. It talks about the bit that I use. It comes from Harbor Freight, and you can get one that is actually just a router inlay bit, but it's really just a 2 flute end mill with a 0.125 radius. And here's all the settings or measurements of that bit that you'll need to put in. They're also up here, and we're going to reference up here, and we're going to reference that information to put in the bit right now. So we're going to go ahead and create an adaptive clearing, which is the first type of cut we need to make. I'm going to click on adaptive clearing. I'm going to go ahead and I'm going to select a bit. See, none are selected now, but once you've created some bits, you can share them between files. I'm going to show you how to make a new bit now though. So I click on bit, and here it wants to know the cutter. So I'm going to look at that file I showed you before that looks like this here, and I'm going to type in those values into the bit. So some important values in the bit that we'll talk about. The diameter is 0.125, or 1/8 of an inch on the bit. The shoulder length, or the cuttable length, is 1.2 inches. The flute length, the length of the flutes or the spirals on the bit, are 1.035. The shaft diameter, the part that's actually held by the router itself, is 0.25. The body length is 1.625. And the overall length of the bit is 3.125. From there, I can just go ahead, I need to make sure I select flat end mill, which is the type of bit that it is, and the number of flutes needs to be 2. It is a clockwise rotation. All the other settings stay the same. I'm going to click OK, and then I'm going to click OK. Now, I'm going to reference the settings over here again. In here, in the tutorial, a little bit of notes about it. First, all settings that are not outlined in the tutorial, if they're not written here, they are considered to be the default. And that default is controlled by the tool selected. Fusion itself knows values and has data based upon tool diameters and materials and things like that. So it'll all be controlled by that tool setting. If the toolpaths happen to get red or error, you can regenerate the toolpath by regenerating it by right-clicking and going to regenerate. So I'm going to go ahead. I am now down here where I'm setting up the feeds and speeds, and I'm just going to represent or reference these values over here. First, spindle speed, 10,000 RPMs. Where's that 10,000 come from? Well, actually the router here on our mill does not have the ability to have an adjustable speed. It is a set speed. It is actually a lot faster than 10,000 RPMs, but as you saw when I typed that value in, the surface speed right here adjusted with that value. So I like, I'm setting it at 10,000 because all the other values that run off of there are a good value or a good number from 10,000 RPMs. The spindle speed is the speed in which the bit itself actually spins. If you ever wonder what anything in Fusion means, if you hover over them, they will give you the meaning of whatever the value or data it wants is. So the spindle speed is how fast it's spinning. I have that set at 10,000 RPMs. I also have it set at the same speed when it's ramping or cutting down into the material. The cutting feed rate. What is a feed rate? It's how the bit moves from side to side, back and forth. It's not how it spins, but how it moves. We're going to adjust the feed rate to about 60 inches per minute, and that's how fast we want the bit to be moving side to side, and all these other values kind of just stay with that. The lead-in feed rate is also going to be 60 inches per minute, and that's a pretty good feed rate. It's kind of faster than what the default is, but we're using balsa wood, a very soft material, so it's fine to really run at 60 inches per minute. We're going to set the ramp feed rate, or when it's coming down in the material, at 20 inches per minute, or a little bit slower because it's doing a little bit more work. And we're going to set the plunge feed rate, where it also plunges down in the material, at 20 inches per minute because that's a little more stress on the bit. We're going to move on to geometry, and at this point it wants to know, what am I going to cut? I'm going to cut I'm going to select a selection. I'm going to select what I want to cut, and I want to select everything inside the boundary box. So I'm going to cut inside of what I want to select, and you'll see here I'm going to select the two holes that I'm cutting out and the chain right there that you can see that selects everything on the sketch. And I want to cut inside those selections because that is my 0. That is the important value. On this bottom cut and anything contained inside like this, you want to keep it an inside containment like you can see here. Now it wants to know heights. So how all the heights pretty much stayed the same, but the bottom height. The bottom height is determined by the length of the bit. So from the stock top, so this top of the piece of wood, we can only cut down negative 1.1 inches, or the bit shoulder was 1.2 inches, but I'm setting the value at 1.1 to be safe and add a margin of error there. So negative 1.1. Passes, we're going to leave everything set at the same right here. It's just you want to double check to make sure stock to leave is set at 0.02 inches, and we're going to leave 0.02 inches there on this cut so that we can come back with the fine cut and clean it up to the final size and have some material to cut away as we do that fine cut. Under linking, the only thing we need to change is the ramp type from helix to plunge. The helix is a complex thing where it spins in a spiral, as a helixal spiral as it runs down into the material. And because we're only using balsa wood, it is fine to just plunge right ahead in there. And then from there, I just click OK. From there, you can see it's now adapting or creating that toolpath for that adaptive one. And here you can see it's still kind of thinking, and it just magically creates, and it knows how to do that. It's creating all those toolpaths and processes. So that toolpath is done now. If I wanted to, I could right click and go to simulate. I can actually preview and watch the toolpath do exactly what it would do, step by step by step the whole way through, and that's an option that you can see there for each of the toolpaths you'll create. So for the bottom cut, we're going to have two processes. We have an adaptive, and now we're going to add a parallel cut. So I'm going to click on, make sure bottom cut selected. I'm going to click on parallel. And from parallel, you can see all of my settings are pretty much saved from the bottom adaptive cut. So that's good. I can just leave those selected and saved. From there, I'm going to move on and select my geometry. You You want to make sure that those values are correct, but they should be saved and the same. My machine boundary again is going to be selection, and it's going to be inside the boundary box again, and I'm going to select that same geometry that I selected last time, the outside sketches of the 3 chains here, or whatever you had selected on your bottom. The same as before, the only height that's going to be changed is stock top, and the length of the bit is negative 1.1 inches, and then from there I'm going to move on to passes, this time under passes. 0 degrees means it runs with the x-axis 0, so side to side like this. If I ran it at 90 degrees, the parallel pass would run in this direction. You could run it either way. I find the best way to run it is in the 0 direction. You get very good results. And the step over, and you can see here by hovering over, the step over option is how much the bit overlaps between each pass. Okay, so the end mill bit, how much it overlaps between each pass. We want that value to be somewhere, it's defaulted at 50%, we want it to be closer to 20% for high detail. If you're trying to mill a car quickly or something else, you could change that value, but 20% is a good value, and 20% of 0.125, the diameter of the bit, is 0.025, is that 20% value, so I'm going to set it right there. And then I'm just going to move over and check the linking, and everything pretty much stays the same there, and I click OK. From there, that parallel cut is going to go ahead, and you can see there how that parallel cut runs. It runs side to side. I'll go ahead and simulate that cut for you for a second, and you can see it just moves side to side and back and forth, and fine cut and cleans up the car. And that's what that cut is for, is like I said, the fine or detailed cut. Alright, I'm going to stop that simulation. Now we're done with the bottom of the car. Remember, in the bottom of the car, in the bottom cut, the Z is facing up, away from where we're cutting. Well, we're now going to cut, by flipping the car over, we're going to cut the driver's side, of the car first. We are going to create the driver's side cut. So to create that driver's side cut, we're going to go ahead and go to new setup. We have the bottom cut done. We're going to create a new setup with a new orientation from that 0 origin point, or the cartridge hole. Remember, every time we're doing that, we're referencing this drawing. X positive, Y positive, Z positive. Y is always out the back of the cartridge hole, but now the Z is going to change from out the bottom to out the side of the car, or the driver's side, and you'll see that here in just 1 second. So, setup, new setup. Operation is milling. We're going to change the orientation to select X and Y axis select Z and Y axis like before. Origin, we're going to select the point just like before, select the back of the car. But this time, the Z axis is going to be, instead of, it's going to be parallel with those axle holes. See that? Parallel. So now Z is facing away from the car on this left side instead of away from the bottom of the car, or perpendicular to the axle holes. And Z is the right way, but if it wasn't, we could flip it back and forth right here. Okay, and now we need Y to be out the back. Well, Y is facing up. So right now it wants me to select the Y axis. That's what it's asking me for. So I can rotate to where I can see a line perpendicular to the axle holes. And now Y is out the back. And if it wasn't out the back, I could flip the Y the same way. Once I get Z away from where I want to cut, this side, Y out the back, and X will kind of just follow along, I need to select the stock like before. Select stock from solid like before, select the stock sketch, click OK. Now we have setup 2 where X is facing away, Z is the side we want to cut, and Y is right there. I can then rename that setup to be driver's side. I like to use this, like I said, because I see driver's side. I don't get confused about left and right. I know which side of the car I drive on. I'm then going to create an adaptive clearing cut for the driver's side itself. This time I'm going to go ahead and go to adaptive clearing. You can see I'm pointing the right way this time. I'm not pointing from the bottom. My bit is over here. All my settings have stayed from before, which is great. I just want to double check them again. Go on to geometry. This time I'm going to go to selection. as I go to selection, this time I do want the tool outside of the boundary box. And you can see why here. I want that tool to go outside of the boundary box to overlap everything to make sure I don't miss any material, because I'm cutting the entire block away. So for these side cuts, I do want to go outside the boundary box. Okay. And as I go outside the boundary box, I want to make sure I select this time, instead of the geometry actually on the car, I want to make sure I select that sketch that I made that is side cut contain that you see right here. So now I've selected, I'm going to cut out just outside of all that geometry right there. I'm going to go on and select height this time, and this time again all I have to change is the bottom height, just like before. But I'm going to select the bottom height from the stock top, but this time it is not going to be negative 1.1 or the bit height. This time it is going to be negative 0.85, or halfway through the car, or actually just past halfway, with a few thousandths of an inch of extra, just to make sure that there's no leftover material. It just overlaps a tiny little bit. Then from there I go to passes, and everything stays the same, just double checking stock to leave at 0.02. And then I go to ramp type again and select. There I have everything selected and I'm good to go. I just select OK. From there, the adaptive pass for the driver's side will start to update. You can see it's a little bit different. It does have some material to cut away, and it's just going to be thinking there for a few seconds and create that adaptive cut for the side. You can see how smart and intuitive this software is. It really is able to create complex toolpaths for very complex geometry. Now I'm done with that adaptive cut. From there, I'm going to need to create the actual parallel cut or fine cut for the side. Make sure the driver's side selected, select parallel just like before. All the settings should stay the same for the tool, just make sure they are, and the feeds and speeds. Select selection for machine boundary, select that side cut contains sketch again. Tool outside boundary just like before, and then the bottom height is going to be stock bottom negative 0.85. The passes, just like before, will be left at 0, but the overlap will be 0.025 inches. And the linking and everything will be just left the same like before. Click OK. This pass will update, and here you can see this very fine pass where it runs up the car. I'll actually simulate this one for a second so you can see it. As it simulates and I run the pass there, and be careful simulating on very slow computers. It does take a lot of work for the car to actually be simulated, but you can watch here and watch this simulation, and you can see the actual toolpath running from the front to the back of the car. So I'm going to go ahead and I'm going to stop that simulation. Now that the parallel cut is done for the driver's side, we're going to go ahead and add the path or tool path to drill the holes. We're going to add a drilling process this time. So I'm going to click drill. Same tool selected. It needs to know the retract feed rate. We're going to set that at 20 inches per minute too. All the other settings have already come from our preset feeds and speeds from before, from our other passes, but we'll just add that one in and double check to make sure they're all still the same. Geometry, it wants to know which holes we're going to actually drill. 1 and 2. Okay, then it wants to know the height. This time we're going to go from the model top, which is right here, and we're only going to drill down. Instead of setting it to drill the whole hole, we're only going to set it to drill negative. We're going to set that at negative 0.03125, or 1/32 of an inch. So it barely marks those holes. And why we're doing that is the diameter of our bit is 0.125 inches. But most axle holes and most axles and bearings that we're dealing with are 3 millimeters. 0.125 inches, or the size of the bit, is 3.17 millimeters. So when you're drilling the hole, it's already too big, bigger than it needs to be. So if we just mark the hole with this bit at 1/32 of an inch, barely down in there, we can come back with a smaller drill bit and we use the drill press to drill that hole at the correct size the whole way through. And then from there, we'll know it's perfect and right in the right spot and at the right diameter. And we'll just use that drill to mark that. If we had a more complex mill with a tool changer, we could change the bit and put in a smaller bit or do things like that, but we just don't have that available to us. So the best way to do that is to just mark that hole with a small 1/32 of an inch drill, and then from there it's rapid out drilling. I just click OK, and I'll go ahead and I'll simulate that tool path for you as well. You can see it's just going to come over and drill real quick those holes. That's a real short tool path right there. So now the driver side is done. I'm going to do a file save again to make sure I don't lose my stuff, and user saved. This version description would be more for someone like multiple people working on it, or if you wanted to put a reference file, like instead of user saved, you could say version with drill holes or something like that. I click OK. Now that whole entire driver side is done. The nice thing about Fusion is making this other mimicked or mirrored side on the other side of the car is going to be very easy. So I can just right click on the driver's side tool setup, click duplicate. As I click duplicate, it'll create another driver's side. I'm going to go ahead, I'm going to rename that driver's side to be passenger side. And then from that passenger side, all of those tool paths are already there. But when I click on them, they're kind of backwards and the Z is the same way. You can see they're on the same side as this. It's the same cut. But if I go into this passenger side setup, and right now you can see they both have Z running out the driver's side. Passenger side setup and go to edit. And on the Z axis I click flip. I can flip the Z and the X updates with it, and Y is still out the back to the correct side. I click OK. Now I get that red exclamation I talked about, but Z is the right way. All I do is right click. They're on the wrong side still, as you can see, but if I hit generate, it'll spin that and create them on the other side all by itself. I'm just going to generate all three. So I've generated all three. They are all updated, and you can see there they are running on this side of the car. These ones are running on the bottom, and the driver's side toolpaths are running on the driver's side of the car. So now I have my 8 different toolpaths right here to go ahead and create, 2 for the bottom and 3 for the drivers and 3 for the passenger side of the car. Now I just have to export this code, this NC code, for the machine to understand. So to do that, I'm going to go to Actions, Post Process. Okay, we're going to go ahead and we're going to post process now the files from Fusion itself and send it out so the computer can, or the mill can, understand the code. So we're going to post process this file by referencing the post processor file that I showed you earlier in the tutorial folder in the post processors. So like I said, we're going to reference those files, the post processor folder. So we have the folder selected that has the post processor in it. We hit select. From there we make sure the mill is right here and available. If it's not available, you'll know you have the wrong folder selected. From there I select my output folder, or where I want to send my files to, which is that NC file folder I created. I hit select folder. Now I want to name my program. I'm going to call it Fusion Dragster 2020 bottom. So this is the bottom cut for my Fusion Dragster example. I'm using 2020. So you just want to name them something specific and have bottom, drivers, passenger side in there so you clearly know which side is which. Then from there I have everything selected. I have the bottom cut selected over here. So it is selected. That is what I want to export. And I hit post. As I hit post, it's where I want to send that to. Is again asking me where I want to save it. It is saving right here to the NC file folder, and I select save. And then from there you can see it is now opened up WordPad, and that's all this is a line of N code. N is, or actually G code. N is describing which line of code it is, so just number 110 is code line 110, but then the G is the actual command there that is being executed. And you can see running the whole way down the list here, we do have 200 and 22,000, sorry, 22,000 and 420 lines of code. And that's a lot of code here to create that car, but you can see that was all created not by hand, but by the post processor and Fusion itself. From this point forward, all we want to do is repeat that process for the driver's and passenger side cut. And then from there, you would be able to go right to the mill and see your advisor, me, or your teacher, and whoever, you cut that file from there. Like I said, Fusion is very intuitive and very quick and easy to get going. If you modeled your dragster directly in Fusion, you could modify theoretically stuff here if it was available, like in like dimensions and measurements of your features, and they would update over here most of the time. But since this car came from SolidWorks, I would have to make the changes here in SolidWorks and then remove the car into Fusion. But once all these settings have been set in Fusion itself, each car becomes easier and easier. Fusion's very intuitive and helps understand settings and keep presets to make things just